biggest theorem so far, maybe even the only real theorem, is that K is not computable, right? The halting problem cannot be decided by a Turing machine. And we did see that it is computably enumerable. So the halting problem is it is a set of natural numbers that corresponds to a pretty nice class of sets of natural numbers, not the computably enumerable class. And I understand you haven't quite developed your appreciation for the computably enumerable sets yet, but computably enumerable for us is going to mean that's a pretty nice class, but it doesn't belong to the nicest, simplest class we will consider, the computable sets. And so this theorem shows that the object I suggested we are interested in, the Turing degrees under Turing reducibility, is at least not trivial. You could already decide that by cardinality considerations, because there's only countably many Turing machines, so in any Turing degree there can be at most countably many sets. Here we have an actual set which is different from computable sets, and there's many examples of computable sets. And now, of course, we've seen one strategy for showing that something is undecidable, and this one strategy is proved by contradiction. Suppose it is decidable, do something clever, get a contradiction. Right? That's what the proof of this theorem was like. And in particular, of course, the do something clever part is sometimes hard to achieve. And this it's why there's other strategies as well. Right? If I have A Turing reducible to B, or many 1 reducible to B, or 1 reducible to B, right? Any of the three reducibilities we care about. If it is the case that A is not computable, then B is not computable. Right? Because if B were computable, then combining the decision procedure for membership in B, in each of these cases, combining the decision procedure for membership in B with the computable reduction, you get a decision procedure for A. And therefore, if A can't be decided, then neither can B. So this is now sort of the standard strategy to show that other sets are not decidable. You take the one example you have and you reduce it to other ones. And so I think I wanted to finish my talking about chapter 1 with one theorem of this flavor. One theorem of this flavor which shows that K is reducible to the set we call tot, and the set tot is the set of those indices that correspond to total functions. And I'm certainly not saying that now that this is the last theorem in chapter 1, I'm talking about that all the other theorems in chapter 1 are not interesting. In fact, there is more interesting theorems than this one in there. But there's I think all of the different ideas in these other theorems you already know, and so if you understand these theorems, then you can read these as well. In particular, Rice's theorem is clearly more important than something about total functions, but I wanted to do at least one where I do a reduction like this. Okay. proof. So in order to prove this, and initially I'm going to just ignore the one there and just come up with a reduction. Don't worry too much about injectiveness. And say, okay, I'll define a function phi of xy to be 1 if x is in K, divergent otherwise. Can I do that? I just did. And of course it is a function, but the question is, of course, is it a computable function?
Well, it's computably enumerable, right? So you can't.
It's a function. Right? For a set, we have the notion of computably enumerable or computable, and computable meant the characteristic function is computable. Computably enumerable meant it's the domain of some function. So for a function being computably enumerable doesn't really make sense. You could talk maybe about the graph of the function being computably enumerable.
No, but I mean, K is computably enumerable, so it's the domain of some function, so take some such function.
So there is this is exactly kind of the question I'm asking about. There is this K here. This is not a computable kind of thing, right? X in K is not computable. And therefore, as soon as I write down a function which I'm going to claim, I don't know, did I already claim that it's computable? Let me do it now. This is a computable function, right? So as soon as I make that claim, and you notice that there is something not computable in there, you have reason to be suspicious. And in particular, if I had written down the function remember, up arrow is anything which diverges, right? Come up with a diverge. If I'd written down this function, it's not supposed to be the same. This is not a computable kind of thing. Right? So what's the difference? Well, the difference is the order of the cases. And why does this work? Well, this does not work. That's the question I was asking.
That's what Rowan was saying, because we have K is computably enumerable. If you have the second case holds, then we have that idea that the set is computably enumerable and its complement is, then we could also conclude that the set itself is computable.
I couldn't follow.
Well, if you had the second function, then you'd have a way. Then the complement of K would be computably enumerable. Right?
Well, you have to do a little bit of work, but I'm looking for something really. These are all clever ideas, but there is when I write something down like this and say it's computable, in general, I don't want there to be a big argument involved in whether or not it's computable. You want to see in a simple way that it's computable, because I've argued before, and I've argued before a little bit silly maybe, that like due to Church-Turing thesis, computability is this very robust notion which corresponds to your intuition. You can be a little fuzzy about it. Of course, that's a little bit of a red herring, I think is the expression. Because even if there was no Church-Turing thesis, I still would never start programming Turing machines, because just like ordinary papers are not written in first-order logic and nice formal derivation, there's always this fuzziness in there. So when I say I do it fuzzy because I believe I can by Church-Turing thesis, I'm lying a little bit. I would do it anyway, and you'd be happy anyway too, maybe. But when I write this down, something like this down, I mean something simple to happen, and that means that you should look at it and see how you can compute it. Right? And so if I look at this first one, then I see how I can compute it. I look at it and I say, okay, so there was this computably enumerable thing in there, the x in k, right? This is something which you cannot compute, but you can start trying to compute it. And so in this first case, this correct function, you start trying to compute it, then if it holds, then you can go on doing something else, namely outputting 1. If it doesn't hold, that means you're in the otherwise case, you automatically already had the right behavior. Right? I think it's a lot simpler than what either of you were suggesting. Even though you might be probably right in what you said, it was over my head, too difficult. Right? This was nice and simple. But in this other case, right, you start computing this, and if it never holds, then you're supposed to output a 1. Well, you can't do that in general. In this particular case, you certainly can't do it because that's exactly the unsolvable problem. Does it make sense?
I just had a quick question. You
Sure.
wrote that as a function of x and y.
Yes. And yes, I'm aware. Y does not appear.
Okay.
Yeah, it's not accidental. Because I'm trying to reduce to total functions. And so I want to take some natural number, x, use it as an input for a reduction, and if x is in k, I want the output of the reduction to be a total function. I don't care how it behaves. And the particular total function I picked is always equal to 1. I could just as well, with, it's been a little while since I wrote my notes, but I'm pretty sure the same argument works like this. Then my total function will be the identity function. It doesn't make a difference. If you feel more comfortable with the input appearing in the definition, you put a 1 in there. But that's the way it works. Okay, so everybody happy with this being computable? Okay, well, but that is easy because I guess in this explaining why I didn't care about the y there, I already said most of what the theorem now is about. Because we know that there exists this theorem called either the parameter theorem or the SMN theorem, which says that there exists this function f of x such that phi of f of x of y is equal to c of xy for all x and y. Right? This is not the function f as it appeared literally in the S&M theorem, because then I would say this is computable, therefore it has an index, and it would be the first input for the function in the S&M theorem. But that's fixed, and so I don't have to mention it. I guess I don't have to mention it again like the S&M theorem, that if you fix the first input in some function, then nothing changes. Right? So this is a nice computable function, f, by the S&M theorem. And what property does this have? Well, if x is in k, then phi of f of x is identically 1, which means f of x is a total function. But you notice that for different x's, the f of x really, there's only two choices. Either it's the constant 1 function or it's a nowhere defined function. And so all of these implications, which I wrote down in one direction, they hold in both directions. Exactly when x is equal to k, this function is constant 1. If it's in k, it's constant 1. Otherwise, it's constant undefined. Maybe that's a poor expression. And constant 1 exactly corresponds to the totalness. And so now I believe even more that I could just as well have written y here, because then it would be, it's the identity if and only if you're in k. Okay. And the proof.
How did you get that last double implication?
This one?
Yeah, I see one way, but how do you get the reverse arrow?
Oh, if it's identically equal to 1, then it's total, clearly. If it's total, well, my f of x, right, the f of x corresponds to an index either for a function which is constant 1 or for a function which is always undefined.
Yeah.
And so these two cases for f of x exactly correspond to x being in k or x not being in k. I argued the wrong equivalence again. This is the one you were asking about, right? But if f of x always corresponds to one of these two indices, so to an index for constant 1 or an index for always undefined, it's only total if it's constant 1. As soon as it's not constant 1, it's always undefined, and always undefined is as non-total as you can get.
So f of x that's an index for a function, right?
Yes,
Yeah.
yes. F of it's the defined here, right, by the SMN theorem. There exists a computable function f of x which does this, and it computes the index. F of x is the index for a computable function that on input y computes psi of xy. Did I prove the theorem yet? I pretended to because I wrote down the proof symbol. I'm pretty close.
If you could decide members of toe, right, then you just give it an x, make this function, see if it's in toe, and then you know whether it's a k or not.
Yes. So I've reduced k to tot, but I wrote down 1, 1. And without writing anything more, this is true too, because S&M theorem says you get a 1, 1 function. Remind me again, how did we get 1, 1 in the S&M theorem? What was the simple quick idea that gave you 1 to 1?
Adron strenuous.
Exactly, right? If you have a Turing machine for something, then you can get infinitely many other Turing machines for the same thing by just adding random instructions that don't mention any states before. You will never read these instructions, but you did get other Turing machines. That's that. Okay, so with that, I'll consider chapter 1 done. You should definitely study Rice's theorem and Meyerl isomorphism theorem, but I suspect that you will find that are interesting, but that all of the ideas in there we've already seen. And these are like reduction ideas, diagonalization ideas, and other things you already know, like Cantor-Schroeder-Bernstein theorem ideas come into play there. Okay, so then we move on to a more proper study of computably enumerable sets. Right, I already suggested before that the CE sets are one class we're going to like, and now we're going to come up with, or we're going to talk about them for a while until we see why. So we still remember the definition is set, let's call it WE, the domain of phi E. So writing this definition down, the E's computably enumerable set immediately also gives me a nice enumeration of the computably enumerable sets, because I have an enumeration of the Turing machines, and so I have all CE sets like this, and the first observation we're going to make about them is that or the first observations we're going to make about them is that the computably enumerable sets are already nice in some way, because this is not the only reasonable way to describe what a computably enumerable set is. There's a bunch of different ways, and that makes them a pretty flexible notion. So we say a set A is sigma 0, 1 if there exists a computable relation R of pairs of natural numbers. So this means that this is a subset of pairs of natural numbers such that its characteristic function is decidable, is computable, i.e. if you give me a pair, I run this Turing machine for a while, and the Turing machine says yes or no depending on whether you're in this relation, such that A is the projection of this relation the projection of the relation onto its first coordinate is exactly this. The set of first coordinates for which there exists a second coordinate that's in the relation. And then the theorem is that A is computably enumerable if and only if A is sigma 0, 1. So this is one different way of describing computably enumerable sets, and that this is true. It's actually fairly straightforward, because if A is computably enumerable, then it's the domain of some computable function. Well, how do you describe the domain of some computable function? Well, the domain of some computable function is those x for which there exists a computation on x that holds. Right? So this is saying, so if A is equal to WE, this means that x is in A if and only if so what did I say? This is a nice intuition. There exists a computation that holds such that of this E's Turing machine, and this is how you can write that. There exists an S phi of E S of X holds. I remember at the very last moment in the last lecture, I wrote this notation on the blackboard. Phi of E is the function computed by the ETH Turing machine, and phi of ES was the function computed by the ETH Turing machine, which never taking more than S steps. Right? So what this is saying is, look at the ETH Turing machine. Started on input X, run it for S steps, see whether you stopped or not at this point. If you stopped, then you converge, so your down arrow. If you did not stop, then you diverged up to this point. Or you haven't converged yet, it's better the expression. And so this certainly here, whether or not you have converged by the S step, is a computable thing, right? You start a Turing machine, take S steps. After S steps are done, this is a finite amount of time, look whether you hold it or not. That's a computable kind of thing. And so here I wrote down exactly, X is in A if there exists a natural number such that for that natural number some computable thing is true, showing that if A is computably enumerable, then it's sigma 0, 1. Everybody happy with that? So then we just need to show the other thing, and the other direction is, well, assume A is of the form the x such that there exists a y r of xy, and now R is a computable relation, And now, given that A is of this form, I need to find a computable function where this is the domain. But that happens to be pretty easy, because I can now define the function mu of y of rxy. Maybe I should say, to introduce some more Greek letters, lambda x dot mu y of rxy. Remember, lambda x is just the way in which you say, in this expression I'm considering x the input variable, so it's a function of x to the remainder. And mu of y of some function was the Gödel's mu operator, and Gödel's mu operator says, go and search for the least y such that r of xy is true. And so now there is two good reasons to believe that this object here is computable. One is if you just believe that mu recursive functions correspond to Turing computable functions, and then this is clearly the case. The other is that it's easy to imagine what this Turing machine looks like that computes this. First it inputs 0 and then checks if the relation is true. If it's true, you're done. If it's not true, then you increase by 1. So now you're 1, you check whether the relation is true. If it's true, you're done. If you're not true, then you increase 1 more and you're done, if you find the relation is true. And so you do this search. And if you ever find the relation is true, you hold and you're good. If the relation is never true, you will forever keep searching and you will not hold. Which, in this case, is exactly the behavior we want for a function whose domain is A. Right? The search for such a y holds exactly in the cases that there exists such a y. Okay, so this gives one really nice different representations for these sets, but from it we get a first, not very surprising property I hope, but a first nice property very quickly. The projection of CE is CE. Right? The definition of sigma 01 was projections of computable sets. So the theorem here says that if you project the projection of a computable set, you get the projection of a computable set. And this just follows from the argument you should expect to follow now if you've done other courses, dummy variables or coding two numbers together, right? We did this nice thing about how to code interesting things as inputs of Turing machines, and in particular we coded pairs of natural numbers as natural numbers by a nice polynomial or something like that. And so that is exactly what you do here. If you have, there exists an x, there exists a y, r of x, y, z, right? I'm projecting and I'm projecting again for the relation. This is exactly equivalent to there exists an x, r, x0, x1, z. Right? There exists an x and a y exactly when there exists a pair whose projections are x and y that do it. So projections of CE are CE. Good. Now I would argue that so far we have two nice characterizations of computably enumerable sets. Neither of them really look like something which is computably enumerable. So here comes the next theorem then. That fixes this. If A is computably enumerable, this happens if and only if, well, there's a special case. A might be the empty set. Clearly there's a function that nowhere converges and therefore the empty set is computably enumerable, or A is the range of a total computable function. And now if you look at this, then you could add to this also if and only if A is the range of a computable function. Because if you have a total computable function whose range does it, then you have a computable function as well, because the total computable function is computable. You have a function which nowhere converges, so doesn't output anything, so gives you the empty set. And you can think about it, and by the same idea as we'll use for this equivalence, you can see the remainder of this equivalence. So that means that now I'm just going to focus on this particular equivalence. What do you do? Well, on the one hand, let's do left to right. If A is computably enumerable, right? This means A is equal to WE. It's the domain of the eth Turing machine for some Turing machine E. And now, if I assume A is non-empty, because if it's empty, I'm already done with the left to right implication. If I assume A is not empty, then I can start searching for an element in A. Right? I give 0 as an input to phi of E, and I start running this computation. Now, if this computation holds, at some point this will happen, and I'm done. If this computation does not hold, then I shouldn't forever continue, because I can't decide when I've gone on long enough. So what the trick is now, is what I want to do is give 0 as an input, run it, give 1 as an input, run it, give 2 as an input, run it. At some point, because A is non-empty, one of these computations will hold, and I found something inside of A. And then once I found this, I want to continue and start looking for other things in A. But I cannot put input 0 into my Turing machine and wait for it to hold or not, because I don't know what happens. So the trick is to dovetail all of these computations, to say, give input 0, run the computation for 10 steps. If it holds, you found something. If it doesn't hold, put it aside. Remember that you still have to get back to it. Give input 1, run it for 10 steps. If it holds, you found something. If it doesn't hold, put it aside, keep a bookkeeping. Go back to input 0, run it for 20 steps. If it holds, you found something. If it doesn't hold, go to input 1. Run input 1 for 20 steps. If it holds, you found something. If it doesn't hold, remember that, and give input 2 for 20 steps. If it holds, you found something. If it doesn't hold, go back to input 0 and run it for 40 steps. And so forth. Right? This way you can run sort of all computations partly together, and this way, even though you cannot decide ever you cannot ever decide that 0 is not in A, but if you know there is something in A, this strategy will at some point find it. By just doing sort of all the computations together, right? It's kind of like your computer actually runs both your email and your browser at the same time, right? It runs your browser for a moment, and then it runs your email for a moment. I guess presuming a single core there, but otherwise pretend your Turing machine has 8 cores as well. But beside the point, right? So you can dovetail computations like this, and now you can find an element in A. And then once you found it, then you keep searching for the next element, and you find I should say, so you found an element in A. Well, this now is your output at 0 for the total function you're computing. And then you keep searching for the next element in A, and at some point you find the next element, and this then is the output at 1 for this function. And then you keep searching for the next element in A, and once you find it, it's the output at 2 for this total function. And then you keep running it again, and you find the next element, and that's the output for 3 for this total function. And now you see, I almost have a definition of a total function, which exactly works under the assumption that A is infinite. If A is infinite, then infinitely often I will find the next element. So aside from the dovetailing of all these different computations to be able to do the search, I need one other idea to do this, and the other idea is that for 0 there's nothing else to it. A is non-empty, so you keep running it until you find an element. Then you have an element in A. Now you have no guarantee that there is another element in A. So your search for other elements in A might never terminate. But that's perfectly fine, because now what you can do is for the output 1 of your total function, you say, well, I'm now going to spend 100,000 steps of computation on searching for the next element. If I found the next element, then I output it. If I haven't found the next element yet, I just output the first element again. And if I just outputted the first element again, then on input 2, instead of spending 100,000 steps of computation, I spent 1,000,000 steps on computation looking for the next element. If I find the next element, I output it. If I don't find the next element, I output the same element again. And so this is, in fact, both of these strategies, the dovetailing of computations and sometimes being able to give up a search because you're going to continue a search in for another something later on anyway, both of these are tricks that are kind of common. Yes?
Can that be encoded in a finite amount of instructions? It seems like
Yes.
we're trying to remember what we did on the previous input on the next input. Or how many...
And if no, I'm not trying to remember it. So I guess for full disclosure, on input 2, what I really do on input 2 is, remember, I'm looking for input 2, let's first compute input 0. Put it on the tape somewhere.
Right. Okay.
Do all the work again for input 1. Put it on the tape somewhere. Do all the work now for input 2, and you've written down on other parts of the tape the work for the earlier inputs. So you're not remembering it, you're just recomputing it, which of course, the initial lie in the course. We care about computation, but no practical concerns. Well, the no practical concerns was not a lie. Right? This is clearly not an efficient strategy at all, but we don't care about efficiency as long as it works. Good. One implication down, one to go. The other one is now easy because it's the same idea, right? Right to left. I have that A is the range of, I have that A is empty. Well, if it's empty, take an always diverging Turing machine and you're computably enumerable. If it's the range of a total function, then what you do is this Turing machine, the East Turing machine, on input 0, what it does is compute the total function on input 0. See if it outputs 0. If it does, then you converge. If it doesn't, try input 1. See if the output of this total function on input 1 is equal to 0. If it is, converge. If it isn't, go and look for the next input. So you're doing here, this computation here searches through all possible inputs for one whose output is the current input to this Turing machine. And this search finishes exactly when the number is in the range of this total function, and it never terminates if you're not in there, which is the exact behavior you want. Pretty happy with that? So there's one thing to point out about these procedures that we it's one of these things that every now and then I will point out something like this, even though most of the time I don't really care too much. But other than this disjunction between empty and non-empty, the procedure is completely uniform. Right? Given an index for a Turing machine that does this, from it, in a computable way, I could obtain an index for this total function, presuming it wasn't empty. From an index for this total computable function, you can, in a computable uniform way, obtain an index for a Turing machine whose domain is this function. Right? So the construction both ways depended on the non-emptiness, but other than the non-emptiness, it was the same for whatever function was your input. And so there's a certain uniformity in there, and sometimes this uniformity is helpful for you. Right here we had the existence of an index for a Turing machine which computes this thing is much more obvious than the existence of a computable function that computes this index. But exactly the existence of this computable function here is what made this a reduction, because the reduction needed to be a computable function. So sometimes the uniformity is good. In this theorem, the disjunction here exactly delimits how much uniformity you have and how much you don't have. Okay, so on that same note, there is again a theorem. It's a nice enough theorem, but there's just a simple nice idea involved. There exist functions f and g which are computable such that wx intersect wy is equal to w f of xy, and wx union wy is equal to wg of xy. So this is saying, this theorem is saying two things. Unions and intersections of CE sets are CE, but on top of that it's saying that this intersection is not just CE. The witness to its CE-ness can be obtained from witnesses of their CE-ness in a nice uniform way. And both of these theorems are pretty easy now that we've realized you can dovetail computations, because what do you do here? I guess here you need to dovetail, here you don't even. What do you do here? This computation consists of take your given input, decide whether Turing machine X holds on it. If it doesn't, then you'll never be able to finish this trying to decide it, but you have the right answer. If it does stop, then you start the computation Y on this input, and if it also stops, then both of these Turing machines stop, and therefore you should be in the intersection. I think what I argued is not just the inclusion, but the equality. At least I can't think of anything else to say about that. That's good. Here you need to dovetail, because here what you do, on a given natural number, which you're trying to decide, is it in this union? You need to decide, does one of these two stop? And so you do exactly the dovetailing again. You run this for 100,000 steps. If it holds, then you're in the union. If it doesn't, then you run this one for 100,000 steps. If it holds, you're in the union. If it doesn't, then you run this one for 1,000,000 steps. If it holds, then you're in the union. If it doesn't, then you can alternate between them. And if one of them holds, at some point you will have taken enough steps to come to this holding condition. You're in the union. And again, the reverse inclusion is exactly the same words I just said, so you maybe permute them a little bit, right? There's no new ideas, these things are pretty clear. Okay, so let me just finish this one last theorem. And now we're running out of time, but that means that next lecture I can really start at a nice position. If you have two computably enumerable sets, then there exists A1, this is a common other one, A1 and B1, also computably enumerable, which are like A and B but better. That's to say, A1 intersect B1 is empty, and A1 union B1 is equal to A union B. So A1 and B1 are in some sense the disjointified versions of A and B. And the nice observation, or the trick is that you can do this in a pretty nice, straightforward way. Because, right, how do you come up with A1 and B1? Now, so anything which goes into either A or B needs to go in A1 or B1. And the sort of the intuitive idea of what A1 and B1 are, or one of the choices for it, is to say that, well, A1 consists exactly of those things in A union B that first appear in A. And B1 is exactly those things in A union B that first appear in B. So what do I mean when I say first appear? Right? You, on a given natural number, trying to decide if it's in A1, B1, or neither of them, on this given natural number, you start trying to decide if it's in A union B. We can do that in a nice, computable, nice way. If at some point we find that yes, we are in A union B, then we know that at least one of the computations, the one that shows that you're in A or the one that shows that you're in B, converges. Run both of them at the same speed, at least one of them converges, but certainly one of them converges before the other does. And so the first converging computation, if the first one that converges is then for A, you put it in A1. If the first one that converges is for B, you put it in B1. And I guess you need a tiebreaker too. If they converge at the same time, put them in A1. But you need to make a uniform choice in some sense.
How do they converge at the same time? I thought you were going back and forth, and only one of them. I mean, at any given time.
Converge at the same time is right. Phi of E S of X, where S is the least stage where you converge. That's kind of what I was saying. But if you go back and forth, then you have another order, right? Converging first is a kind of intuitive thing anyway. So pick whatever order you like. I picked the exact number of steps you need to compute, and then you might have the same number. Yeah.